By the mid-1800s, chemistry seemed like a growing catalog of isolated facts. Laboratories across Europe were packed with glass bottles and labels. Oxygen, chlorine, iodine, calcium, sodium, bromine, magnesium, each with its own reactions, boiling points, atomic weights, chemical quirks. Textbooks listed them like a long phone book, one element after another, a laundry list of detached data. There was no unifying map to show how they related. Some chemists began to wonder, were these chemical building blocks really a random collection? Or could there be a hidden order beneath the noise? Might nature hide a pattern that so far no one had glimpsed? This question sparked small but courageous attempts. Researchers compared atomic weights, reaction behavior, and physical properties. They drew large, messy tables by hand. They grouped and regrouped, circled and crossed out. In this trial and error chaos, occasionally a tiny pattern emerged. A set of 3 elements reacting similarly. A recurring similarity in chemical behavior among certain species. These faint clues hinted at something bigger, a map of matter waiting to be drawn. Those small patterns were the seeds of a revolution. This is the story of how scattered data and isolated experiments eventually converged into a powerful organizing chart, the first version of the periodic table, and how one visionary chemist turned chaos into order. Long before anyone thought of a periodic table, there were preliminary efforts at classification. In 1789, the French chemist Antoine Lavoisier published a groundbreaking work. A systematic list of what he considered the basic elements, separating them from compounds. He grouped substances broadly, gases, metals, nonmetals, giving chemists a first rough map. It wasn't perfect. Some substances he listed weren't true elements. The list was incomplete. But for perhaps the first time, chemists could look at a table and think, these may be the fundamental building blocks. Still, Lavoisier's list didn't reveal hidden patterns. It offered classification, but not prediction. That came decades later. In 1829, German chemist Johann Wolfgang Döbereiner observed a curious phenomenon. Certain elements seemed to form groups of 3, triads, with similar chemical behavior. For instance, chlorine, bromine, and iodine were different in atomic weight, but similar in their salt-forming behavior. Calcium, strontium, and barium did something similar among the alkaline earths. Even more curious, the atomic weight of the middle element often sat roughly at the average of the other 2. Döbereiner called these triads. His insight suggested that elements were not a random scatter, but a few small harmonies hiding inside the apparent chaos. Yet there was a problem. Most elements didn't fit into triads. The scheme was elegant but incomplete, a handful of harmonies in a sprawling cacophony. In the 1860s, another voice entered the search, John Newlands. He proposed what he called the Law of Octaves, ordering known elements by increasing atomic weight. Newlands noticed that every 8th element shared chemical similarities, reminiscent of musical octaves. It was bold, a continuous, repeating pattern across elements. For lighter elements, the idea seemed promising. But as more elements were discovered, especially heavier ones, the pattern crumbled. The octaves failed for many elements. The scheme was ridiculed by some contemporaries, dismissed by others as fanciful. The repeating pattern simply didn't hold universally. Still, Newlands' attempt marked a shift, thinking not in lists, but in cycles and rhythm. Chemistry was evolving, not just in knowledge, but in perspective. So by the mid-19th century, chemists had a handful of sketches, lists, triads, and tentative octaves. None offered a universal map, but together they transformed the mindset. The idea that elements might follow a deeper order, perhaps periodic, was no longer unthinkable. The stage was set for someone to bring everything together. That man was the Russian chemist Dmitri Mendeleev. By the late 1860s, the number of known elements had grown drastically, more than 60 at least. Mendeleev, working as a teacher, faced a problem: how to teach these many elements to students so they made sense. A long list of names and numbers felt chaotic. Certainly not a language with grammar. Instead of numbers in a fixed list, he turned to cards. On each card, he wrote an element's name, its atomic weight, as it was known at the time, and its chemical properties. Then, like playing a game, he shuffled, arranged, and rearranged these cards over and over. He laid them out in order of increasing weight, but grouped them by behavior. He stacked them, moved them, compared them. After multiple iterations, something remarkable happened. Elements with similar chemical behavior landed in vertical columns, even if their atomic weights didn't match neatly. Reactive metals grouped together. Halogens lined up. Metals with similar chemistry are clustered. Mendeleev had recognized a pattern, not a strict numerical order, but an order of behavior. He bent the long line of elements into rows, called periods, and columns, called groups. Across a row, atomic weight roughly increased. Down a column, chemical behavior stayed similar. Chemistry gained structure, but perhaps his boldest move came with the anomalies. Some elements didn't fit the pattern exactly. Their chemical behavior suggested they belonged in one group, but their atomic weights said otherwise. Mendeleev trusted chemical properties over raw numbers. He swapped the positions of certain elements, notably tellurium and iodine, acknowledging that the measured weights could be wrong. That choice would pay off. Even more daring, he left gaps in his table, blank spaces that stood for elements that had not yet been discovered. And he made predictions, not vague guesses, but concrete estimates. For each gap, he suggested atomic mass, oxide formulas, density, chemical behavior. One gap he called aluminium, an element he predicted would sit just below aluminium in the table. Aluminium is the gallium of today, which is below, as Mendeleev said. That was not faith, it was science. Mendeleev's predictions did not collect dust. They pointed to real possibilities unknown, hidden in the earth, waiting to be discovered. In 1875, just 6 years after Mendeleev published his table, a French chemist, Paul-Émile Lecoq de Bois-Boudrin, discovered a new metal, gallium. Its properties: atomic mass around 69.7, density about 5.9 grams per cubic centimeter, and a low melting point. A soft metal that can melt in a warm hand, matched Mendeleev's aluminium almost exactly. The prediction was spot on. A decade later, in 1886, German chemist Clemens Winkler discovered germanium, which fit Mendeleev's silicon. Again, the atomic mass, oxide behavior, and reactivity all lined up closely with what Mendeleev had written years earlier. What once seemed like a clever arrangement on paper was validated by nature itself. These successes changed everything. The periodic table was no longer a heuristic or a classroom chart. It was a predictive, scientific tool, a map that pointed chemists toward new elements, undiscovered until then, a modern alchemist's treasure map. History began to view Mendeleev as the father of the periodic table, but the truth is more layered. He built on the ideas of others, but he was the one bold enough to synthesize them into a complete, predictive system. Mendeleev wasn't the only one sensing a deeper pattern. Around the same time, German chemist Julius Lothar Meyer was conducting his own investigations. In 1864, Meyer arranged 28 elements by atomic weight and grouped them according to valence, how many bonds they tended to form. Later, he plotted atomic volume, which is atomic mass divided by density, against atomic weight for many elements. The result was a striking wave-like curve. Elements with similar chemical properties appeared at the peaks and troughs of that curve. Meyer's insight provided a different, more physical dimension to the periodic idea. While Mendeleev's table organized elements by behavior and weight, Meyer's graph hinted at hidden structure in the measured data: periodicity in volume, density, and mass. Yet Meyer stopped short of making predictions. He wasn't willing to leave gaps for unknown elements. In that hesitation lay the key difference. Mendeleev dared to forecast the unknown. Meyer described only what existed. That difference helped tip history in Mendeleev's favor. By around 1870, two independent but complementary frameworks existed: Mendeleev's table with its bold predictions, and Meyer's graph revealing periodic trends in physical data. Together, they strengthened confidence that the periodic law was real, not a coincidence, but a reflection of nature's architecture. By the late 19th century and early 20th century, more elements had been discovered. But some oddities remained. Ordering by atomic weight sometimes forced chemists to put certain elements out of their chemical families, even when their behavior said they belonged together. Some pairs seemed reversed or misordered if based only on weight. Scientists sensed that the periodic table had more to reveal, but they lacked a deeper physical explanation. In 1913, English physicist Henry Mosley provided that explanation using X-ray spectroscopy. He measured the frequencies of X-rays emitted by different elements when bombarded with high-energy electrons. What he found was revolutionary. The square root of the X-ray frequency was directly proportional to a whole number specific to each element: its atomic number, the number of protons in the nucleus. Suddenly, the atomic number became more than a position in a chart. It was a fundamental, measurable physical quantity. With that, many lingering anomalies vanished. Ordering elements by atomic number instead of atomic weight resolved issues like why some heavier by weight elements should come before lighter ones because of their chemical behavior, like the tellurium-iodine pair. Mosley's discovery upgraded the periodic table from an empirical arrangement to a structure rooted in atomic physics, linked directly to the nucleus. It bridged chemistry and atomic science. It showed that the periodic law reflected the very architecture of atoms. Today, we understand why the periodic table behaves as it does. Each element's place reflects its atomic number, the count of protons in its nucleus, which, in a neutral atom, equals its number of electrons. These electrons arrange themselves in shells and subshells according to quantum rules. As you move across a row, or period, electrons are added to the same outer shell. As you move down a column, or group, electrons enter similar valence positions in new shells. This structure explains periodic trends. Elements with a single valence electron, like the alkali metals, are extremely reactive, eager to lose that electron and reach a more stable configuration. Elements with complete outer shells, like the noble gases, are stable, inert, and rarely react at all. Differences in electron configuration explain differences in metallic behavior. Reactivity, bonding, density, ionization energy, and much more. What's astonishing is that when Mendeleev drew his table, none of this, protons, electrons, shells, was known. He used only atomic weights, oxide formulas, chemical reactions, and melting points. Yet, his table aligned strikingly well with truths that quantum mechanics would later reveal. He captured a hidden logic before science even had the vocabulary for it. Mendeleev's periodic table didn't collapse when new discoveries came. Instead, it proved its power by growing. As new elements were discovered, they slipped into predicted places or expanded the table further. Take the discovery of the noble gases. In the late 19th century, gases like argon, neon, krypton, xenon, and helium were found. Elements that rarely reacted, inert and silent. They didn't fit the old chemical families. Rather than reject the table, chemists expanded it, adding a whole new column on the right for these almost inert gases. The periodic law held. In the 20th century, another challenge came with the lanthanides and actinides, a series of elements with similar chemical behaviors and very close atomic weights. To keep the table readable, chemists placed them in two separate rows beneath the main body. It was a visual convenience, not a break in the law. These F-block elements still follow the same periodic pattern because their electrons fill F orbitals, and their chemistry reflects that structure. Then came the age of synthetic elements. Physicists learned how to build atoms in reactors and accelerators with atomic numbers far beyond naturally occurring uranium. Many of these transuranic elements are extremely unstable, decaying in milliseconds or seconds. Yet even these ephemeral atoms fit into the periodic table, sliding into boxes that had been empty. Before they existed, their placeholders were already waiting. The periodic table had charted not only what nature had given us, but also what modern science could build. Through each expansion, through each new discovery, the periodic table remained robust. Its internal logic stayed valid. New families, new rows, new columns, but the rhythm held fast. What started as a teacher's frustration trying to make sense of more than 60 chaotic elements became one of humanity's greatest scientific tools. Today, the periodic table is far more than a chart. It's a blueprint for matter, a guide that lets us predict new elements, design materials, and explore the hidden structure of atoms. When scientists look at the table, they don't just see symbols. They see centuries of trial and error. Lavoisier's early lists, Döbereiner's triads, Newlands' octaves, Mendeleev's bold predictions, Meyer's curves, Mosley's atomic numbers, and the discoveries that filled its final rows. What once looked like scattered facts, atomic weights, reactions, obscure oxide formulas, revealed a deeper rhythm, a pattern woven into the universe itself. And that pattern still matters. Chemists and physicists use the table every day to predict reactivity, create new compounds, and even build synthetic elements that live for only fractions of a second. From medicine to materials science, it remains a universal guide. In a simple grid of letters and numbers, it connects hydrogen, the lightest atom, to super heavy elements forged in particle accelerators. A continuous story stretching from ancient alchemy to modern nuclear physics. The periodic table is more than a scientific chart. It's a story of curiosity, insight, persistence, and the belief that nature follows patterns. So the next time you glance at those little boxes, don't see just names. See centuries of experiments, mistakes, breakthroughs, predictions that came true, and the stubborn hope that the universe can be understood. And remember, even when knowledge looks scattered, with curiosity, imagination, and the courage to follow a pattern, we can turn chaos into clarity. We can chart the unknown. We can uncover the hidden architecture of matter itself. Thanks for watching, and until next time, keep asking why.